This is session C1, the wave mechanics of matter waves from 1925. Last session, B8, we covered complex numbers and complex exponentials, which we will need for this lecture. In this lecture, we will discover, develop, justify the Schrödinger equation. Erwin Schrödinger was an Austrian physicist teaching and working in Zurich, Switzerland in 1925. He was 38 years old, 8 years younger than Einstein. We can't actually derive the Schrödinger equation from classical mechanics, even using the Dubrow relation, nor can we prove it. We should say that Schrödinger developed the Schrödinger equation, and the justification for it was only in solving problems and comparing results to experimental results. Why have this lecture on discovering the Schrödinger equation? You might feel you should just jump right into the Schrödinger equation in the next lecture, where the Schrödinger equation is just given to us as revealed truth. But why does it have that form? And why the heck does it have that imaginary number I in it? And why do we need to use complex numbers and complex exponentials? Watch this video to understand these things. If you're not comfortable with why that imaginary number I is in the Schrödinger equation, you should watch this video or get comfortable with it. We will see why the Schrödinger equation includes the imaginary number I and why quantum mechanics uses complex numbers and complex exponentials. In this lecture, I will need to use some calculus, but I will provide it for you. It's fine if you don't know calculus. You should still be able to follow much of this lecture, but you will have to trust me on the calculus parts. This lecture has 8 sections in it. Free particle in one dimension according to classical mechanics, Dubrow matter waves, what is a wave equation, some derivatives that we need from calculus, developing the wave equation for matter waves, developing the non-relativistic wave equation for matter waves, the Schrödinger equation, energy levels for a free particle, and how is the matter wave a particle really? This is a possible time to take a break. We'll start with a free particle in one dimension according to classical mechanics. And what do we mean by this? One dimension, the particle will have motion only in the plus or minus x direction, and we will be able, since we can choose what is the plus x direction, we will choose it to be in the same direction as the motion. So we will only have motion in the plus x direction. We don't have to do that, but it simplifies several things, and so we will do that. So we will have no motion in the y or z direction. It's a particle. It has mass, and that mass is not zero. The particle is point-like, or if you don't want to think of it as a point-like, if you want to think of it as having size, then we are only going to be concerned with its center of mass, which is point-like. We will not deal with any rotation of the particle, nor any internal vibration. It's a free particle. By that we mean that there is zero net force acting on the particle. It has constant potential energy, which we can therefore take to be zero potential energy. There is no acceleration, therefore its velocity is constant, and its momentum is constant and definite, momentum p. So momentum squared is constant. Kinetic energy is constant, and total energy is constant. So the simplest possible case that we could deal with in classical mechanics. Should our treatment be relativistic or non-relativistic? Einstein published special relativity in 1905. Younger physicists were certainly comfortable believing and using special relativity by 1925. The Schrödinger equation is non-relativistic, but actually Schrödinger's first wave equation was relativistic. So we're going to explore both relativistic and non-relativistic in this lecture. We're only going to need the formula for relativistic energy, so we're not going to deal with other aspects of special relativity, which are pretty confusing. We'll be able to use a fairly simple result. But nevertheless, if the relativistic part of this lecture is really confusing for you, ignore those bits and continue with the lecture. The Schrödinger equation, which is the only equation we will use after this lecture, is non-relativistic. This lecture will help us see why we use it. The relativistic total energy satisfies this formula, that the energy squared equals the mass squared times the speed of light to the fourth plus the momentum squared times the speed of light squared. When we're dealing with non-relativistic cases, we can look at the kinetic energy, E, because there is no potential energy. This is a free particle. The kinetic energy is 1/2 mv squared, which can be written, and we will write as momentum p squared over 2m. And that must be much less than mc squared for a non-relativistic case. We could distinguish between this energy and this energy, which are not the same. We could give them different labels, but I'm not going to do that. I'm going to call it E for energy in both cases, but I will always tell you I will always identify whether we're using the non-relativistic kinetic energy or we're using the relativistic total energy, but I will call them E in both cases. This is a possible time to take a break. Dubrow matter waves. In lecture B5, we covered a little bit that Louis Dubrow's 1924 PhD thesis postulated wave-particle duality, that a particle with mass can exhibit wave-like behavior, diffraction, interference, as light waves do. Dubrow worked from Einstein's 1905 theory of special relativity and Einstein's 1905 explanation of the photoelectric effect as light being a quantum that we call a photon. Dubrow's theory of matter waves was a relativistic treatment, but you won't get that impression from an undergraduate quantum mechanics book. They will use the Dubrow relation in its non-relativistic form, and that always confused me. We will see this. Dubrow's matter waves are not a physical displacement wave like a water wave or a sound wave, and they're not electromagnetic waves. They're something different. The matter wave will turn out to be a probability amplitude wave function, but we don't know that in this lecture. So we will develop a matter wave equation without yet knowing what the wave function means. We will get that when we have more experience in other lectures. For a free particle, the momentum is constant, a definite value. From Dubrow's relation, we get that the matter wave wavelength lambda is Planck's constant over the momentum, where the momentum has a definite value. This comes from Planck's black-body radiation work in 1901 and Einstein's photoelectric effect in 1905. The wave frequency of the matter wave, F, would be the energy E over Planck's constant. This comes from E equals hf, which you'll recognize from Einstein's photoelectric effect paper. I chose not to include this in the earlier material in lecture B5 because it has some issues. In Dubrow's paper, E was the total relativistic energy. But we're also going to want to see what happens if E is the non-relativistic kinetic energy. We know the frequency. What is the angular frequency, omega? It's 2 pi times the frequency. So energy times 2 pi over Planck's constant. Well, that's energy over h bar, where h bar is the reduced Planck's constant that we've seen before. So those are the Dubrow relations that we will need to investigate matter waves. This is a possible time to take a break. Now we need a possible matter wave function. And waves consist of sines and cosines of some phase, phi, and we can make a linear combination of sines and cosines, and we will take our possible matter wave function to be this: capital psi, Greek letter psi. We will always capitalize it when we're including time. So for a free particle in one dimension, capital psi of x and t will be some constant a times cosine of a phase, and that phase will be wave number k times x minus omega t, where wave number k is 2 pi over lambda. So the phase here is 2 pi x over lambda minus omega t, and we also have the sine term, b times sine of the same phase. Now, in choosing a minus sign for the omega term, we chose this wave to be traveling in the plus x direction, positive momentum. We chose the positive x-axis to be in the same direction. So the wave number k will be positive. The wavelength lambda would always be positive, but by choosing the x-axis in the same direction of momentum, we don't have to worry about the wave number having a sign. The angular frequency omega is always positive. Now, so for a given phase where phi is constant, if we advance time, we're advancing position x. So the wave is traveling in the plus x direction. Now, let's substitute the Dubrow relations for this matter wave. We had a Dubrow relation for lambda, and we had a Dubrow relation for omega, so we're going to substitute them in. So lambda was h over p, and omega was e over h bar. And we can rearrange these, and we get a phase of quantity momentum times position minus energy times time, quantity over h bar. A and b are constant, but they could be complex. We don't know yet what those will be. This is a possible time to take a break. We would like to use our assumed wave function, psi, for a free particle in one dimension to guess or discover a wave equation governing matter waves. Schrödinger initially thought that the Dubrow thesis was nonsense, but he saw that Einstein took it seriously. Peter Debye asked Schrödinger to give a colloquium report, a seminar report, on Dubrow's thesis. So Schrödinger worked to see what Dubrow's work could mean. After Schrödinger presented Dubrow's thesis, Debye thought that Dubrow's presentation was rather childish. He said that to deal with waves, one needed a wave equation. 2 days later, Schrödinger had discovered the relativistic wave equation for matter waves. But later we will learn that this had some problems. We will learn more in this lecture. This is a possible time to take a break. What is a wave equation? A wave equation is a partial differential equation involving partial derivatives of some function of space and time with respect to space and time, where the relationship between the derivatives creates and reinforces the periodic sinusoidal behavior of the wave. Now, if you don't know calculus, don't quit yet. I know that you're not familiar with these things. A derivative is a derivative of a function with respect to some variable, like position, is saying, well, how is that function changing with that variable position? So a rate of change. Or if we graph the function, it's the slope of the tangent at that point. I will explain partial derivatives in a little bit. And a partial differential equation is an equation, so a left side and a right side that are equal, but the left and right side have partial derivatives in them. So you won't be familiar with this, but that's okay. Trust what I'm doing and see what the results are. When we take a partial derivative with respect to one variable, for example, time, we hold all other variables, for example, positions x, y, and z, constant. So it's actually easier to do than we might think. It's easy to treat something as a constant. Once we have the wave equation, solving the wave equation determines valid functions that represent waves, which is what we want to do. We want to know what wave functions are for particles, and we need a wave equation that we can then solve to find valid functions, valid wave functions. Here's the one-dimensional wave equation for an electromagnetic plane wave traveling in the plus or minus x direction. It involves electric field. E of x and t is the electric field amplitude in a perpendicular direction to travel. So if we're traveling in the x direction, the perpendicular direction might be y. If we do the second derivative of the electric field with respect to time, so we do how much is the electric field changing with respect to time, and then how much is that changing with respect to time, the wave equation says that must be equal to the speed of light squared times the second derivative of the electric field with respect to position. So how much is the electric field changing with respect to x, and then how much is that changing with respect to x? There would be a matching wave equation for the magnetic field, but we don't need to see that. So if you're not familiar with calculus, this will look totally foreign. There's nothing we can do about that. But if we ignore that, it's not that complicated an equation. It has one term on the left side, one term on the right side. If we can find an electric field that satisfies this equation, that's a valid electric field, a valid electromagnetic wave. This is a possible time to take a break. Some derivatives we need from calculus. Well, first we need to know what a derivative is, and I know some of you know this very well, but others don't. So the derivative is, we could think of as the slope of a tangent at a point. The green curve here is a sine wave, sine of x. The red curve is a cosine of x. Let's take the sine wave, and at this point, x equals 0, we look at its slope. Well, its slope is actually 1 at this x equals 0. And that is also the value of cosine of x at x equals 0. What's the slope at x equals pi over 2? Pi over 2, the sine wave is a maximum. It's at its peak, and its slope, its tangent, has a slope of 0. And that is also the value of the cosine at pi over 2. At x equals pi, the slope of the sine wave is -1, and the value of the cosine is -1. It turns out that the derivative of the function sine of x is cosine of x. We're not going to prove that, but it's true, and you can learn more about that from videos on Khan Academy or looking on Wikipedia or a calculus book. Now we're going to take some derivatives that we will need later in this lecture. If we have sine of constant a times variable u plus constant b, and we take the derivative of that with respect to u, we get constant a times cosine of au plus b. If we take the derivative of cosine, we get minus a sine au plus b. Now we will need to take second derivatives. If we take the second derivative of sine of au plus b, it's taking a derivative of the derivative that we already took. The first derivative of sine with respect to u is a cosine of au plus b. And if we take the derivative again, we get minus a squared sine of au plus b. If we take the second derivative of cosine of au plus b, we get minus a squared of cosine au plus b. Now these are important results for waves, that if you take the second derivative of the sine, you get the sine again with this multiplicative factor of minus a squared, which is a constant. And if you take the second derivative of cosine, you get cosine again with a multiplicative term of minus a squared. The fact that the second derivative turns sine into sine and cosine into cosine, and the second derivative shows up in wave equations, is why sines and cosines are waves in these wave equations. It's going to turn out to be a little bit different for the Schrödinger equation, and that's part of the purpose of this lecture, is to find out, well, why is that different? We need one other result. If we take an exponential function, e to the au, where a is a constant and u is a variable, and we take the derivative of that with respect to u, we get a times e to the au. And it turns out that's true whether a is real, imaginary, or complex. Now, that's all the results we'll need from calculus. In the rest of the lecture, we'll be substituting some of these, but we won't be doing new derivatives. So that's all the calculus results we will need. This is a possible time to take a break. Let's develop the wave equation for matter waves. Let's assume that as we did before, that the matter wave function, capital psi of x and t, is a cosine phi plus b sine phi for a free particle in one dimension, where that phase is, as we discovered before, quantity p times x minus e times t over h bar. And a and b are constants that could be complex. We don't know yet. First, let's take the partial derivatives of the phase phi with respect to t and x. This is a simple derivative. So the partial derivative of phi with respect to time is minus e over h bar. Here's time, and it gets multiplied by minus e over h bar. So that is the first derivative of phi with respect to time. The first derivative of phi with respect to x is p over h bar. Now let's take the first partial derivatives of the wave function psi with respect to t and x. And to do that, we're going to use the earlier calculus results we had. We showed earlier how to take the derivative of a sine and the derivative of a cosine. So we're going to substitute those results. So the first partial derivative of psi with respect to time is minus e over h bar times the quantity minus a sine of the phase phi plus b times cosine of the phase phi. You can work that out just using substitution from the earlier results. The first partial derivative of psi with respect to x is plus p over h bar times minus a sine phi plus b cosine phi. Now we want to take the second partial derivatives with respect to t and x. So we take the derivative again. The second partial derivative of psi with respect to time is energy E squared over h bar squared times minus a cosine of phi minus b sine phi. We could pull this minus sign to the front and notice that a cosine phi plus b sine phi is the same as psi. So we get that the second partial derivative of psi with respect to time is minus e squared over h bar squared times psi. We do the same thing with respect to x squared, and we get minus p squared over h bar squared times wave function psi of x and t. Let's rearrange these equations as follows. E squared times psi is minus h bar squared times the second derivative of psi with respect to time squared, and p squared psi is minus h bar squared times the second derivative of psi with respect to x squared. We saw earlier that the relativistic total energy satisfies E squared equals m squared c to the fourth plus p squared c squared. the energy is squared, which it also is here. Momentum is squared, which it also is here. So if we multiply both sides of this equation by psi of x and t, we get, just tack on a psi on both sides, e squared psi equals m squared c to the fourth psi plus p squared c squared psi. But now we can substitute. Here we have e squared psi, and there we have e squared psi, so we could substitute this for that. Here we have p squared psi. Here we have p squared psi. We could substitute this for it. So let's substitute for those, and we get this equation. We substitute it on the left. We substitute it on the right. Let's rearrange this. We put everything on the left side, and we divided by minus h bar squared c squared, divided all the terms by that. We get 1 over c squared times the second derivative of psi with respect to time minus the second derivative of psi with respect to x plus m squared c squared over h bar squared psi equals 0. This is the correct relativistic wave function, wave equation for a free particle in one dimension. But this is not the Schrödinger equation. What happened? Why did we get a different equation? And why aren't we using this in quantum mechanics? And how do we get the Schrödinger equation? This is a possible time to take a break. We will see that, but we will work at it a little so that we get some understanding of why we're not using this equation, why we are using the Schrödinger equation, why does the Schrödinger equation have the form it has, and why is there that pesky I in the Schrödinger equation. We will get that information in the rest of this lecture. Now, Schrödinger had developed this relativistic wave equation within 2 days of Peter Debye saying that a wave equation was needed for matter waves. He took this relativistic wave equation for a free particle in one dimension, extended it to 3 dimensions, which is easy to do. He added in the potential energy, which is easy to do, so the equation would not just be for free particles. He solved for the energies of the electron states for the hydrogen atom, and he got the correct results for the Bohr energy levels of hydrogen. And history thinks that he was off by a factor of 2 for what are called the fine structure corrections, which are about 0.01% corrections to the energy levels, which were known experimentally by 1925. Now, I say history thinks because Schrödinger did not actually write down in a journal why he gave up on this equation. He chose not to publish this version, the relativistic wave equation, and his results for hydrogen. He moved on, and if he wrote down his reasoning, that is lost to history. He then developed a non-relativistic wave equation that we know of as the Schrödinger equation. He developed that over a period of about 6 weeks over a Christmas holiday and then published it. We'd like to see how to come up with a Schrödinger equation. We won't use the same procedure that he did, but we will have a valid understanding of the Schrödinger equation. Now, Schrödinger's relativistic wave equation did not give the correct fine structure corrections for hydrogen because in 1925 it was not yet appreciated that the point-like electron has an internal intrinsic property, which will later be called intrinsic spin angular momentum. Don't worry about that name for now. And it turns out that property contributes to the fine structure corrections, and that wasn't appreciated by Schrödinger when he did his solution for hydrogen using the relativistic equation. So he abandoned it. Electrons always have spin angular momentum. You can't make the spin of a single electron go away. Some problems take the electron spin into account, and other problems are able to neglect the contribution from electron spin. It is confusing for a new student to know, well, when is it needed? When is it not needed? You know, it's confusing. We need to get experience in order to appreciate that. We will get some experience. We don't need that in this lecture, however. So the relativistic wave equation we call the Klein-Gordon equation. Schrödinger didn't publish it. He abandoned it. Later, Klein and Gordon did publish it, and we know it by that name. Once the corrections for electron spin were known, we should be able to use that relativistic wave equation. Why do we still use the non-relativistic Schrödinger equation instead of learning and using the Klein-Gordon equation? Every time you use the Schrödinger equation, we should ask ourselves, okay, well, is this result still non-relativistic? Is the speed of the electron still much less than the speed of light? You know, wouldn't it be easier just to use the relativistic equation and not have to worry about this? And the answer appears to be no. The relativistic wave equation, it poses a difficulty in interpreting time evolution that's not present for the Schrödinger equation. It's because the Klein-Gordon equation has the second derivative of time, and we'll see that the Schrödinger equation has the first derivative of time, and that makes it easier to understand the time evolution of wave functions. Also, to use the Klein-Gordon equation, the definition of probability density is more complicated than for Schrödinger equation. Physics students take 1 to 3 semesters of undergraduate non-relativistic quantum mechanics, Schrödinger's equation. Some students later will take a graduate relativistic quantum mechanics course, and then they will move on to quantum field theory and other subjects. But as far as I know, undergraduates learn Schrödinger's equation, and we will stick with that. That's what we will need to learn, and we still need to develop that equation because we don't want to just take it as a given. We want to see how it comes about. The Klein-Gordon equation was easily obtained because the relativistic energy equation was second order in both energy, E squared, and momentum, P squared. But by being second order in energy, it means that the Klein-Gordon equation had a second derivative of time, which is harder to interpret correctly than the first order first derivative of time that we will get in the Schrödinger equation. Now, if you take that Klein-Gordon equation and you turn the mass to 0, like for photons that are massless, and you replace psi, wave function psi, with electric field, you will get the earlier wave equation for the electric field. The wave equation for electromagnetic fields, it had to be relativistic. Light travels at the speed of light. But even though they're similar, wave function psi of x of t is not a vector quantity like the electric field. This is a possible time to take a break. Now let's develop the non-relativistic wave equation for matter waves, the Schrödinger equation. Let's try to develop a non-relativistic wave equation for matter waves. We hope that the time derivative will be first order for a straightforward time evolution of the wave function, and it will be. We saw earlier that for non-relativistic kinetic energy for a free particle in one dimension, kinetic energy E is p squared over 2m, and this has to stay much less than mc squared in order to be non-relativistic. So somehow we're going to have to turn E equals p squared over 2m into the Schrödinger equation. Let's assume the same matter wave that we did before. Cosine and sine, constants a and b, the same phase, px minus et over h bar. And let's see if we can get the Schrödinger equation. We previously worked out the first derivatives of psi with respect to time and position. The second derivative of psi with respect to x was minus p squared over h bar squared times psi. We did that before. P squared psi is minus h bar squared times the second derivative with respect to x squared. Did that before. So we want to find the wave equation starting from E times psi equals p squared over 2m times psi, non-relativistic. And we know p squared psi, so we could substitute it in. And we get that E psi equals minus h bar squared over 2m times the second derivative with respect to x squared. If you already know Schrödinger's equation, this is starting to look familiar, but I'm not going to assume that you do know Schrödinger's equation. Now, let's assume that we will be able to find somehow that E times psi is a first partial derivative of psi with respect to time times h bar times some constant a, which we don't know yet, but we want to determine it. This little a is not the capital A that we used earlier. So we're going to make an assumption. We're going to see if we can find a consistency later. If we could find this to be true, then we would have a wave equation. This is a possible time to take a break. Let's plug psi of x and t into this equation. So we're going to keep E psi on the left side, but we're going to do the first derivative of psi with respect to time on the right side. and keep this factor of a times h bar. So a times h bar, we already did the first derivative earlier, so we can substitute it in. Minus e over h bar minus a times sine phi plus b cosine phi. We can rewrite this constant, well, in this prefactor, h bar and h bar cancel. We can move the minus sign out. We get a times e, but we already know that we want e to be equal to p squared over 2m. So we get that somehow we hope that we can end up with e times psi is this expression. Minus a p squared over 2m times what's in the parentheses here. Now, we already know that p squared over 2m times psi is this, p squared over 2m, and this is psi. So in order to get a wave equation, we need this expression for e psi to equal this expression for p squared over 2m psi. But they're not obviously equal. I mean, this has a on the sine term, this has a on the cosine term, this has b on the cosine term, this has b on the sine term. So they're not trivially equal, but the e equation has this factor of a in it, and that makes the difference. That can get us there. These two equations can be equal if we can get this sine term to match this sine term. Now they both have a p squared over 2m, so we can ignore that. So what we need is minus little a times minus big A to be equal to b. Then they would be equal. So if little a times big A were equal to b, and minus little a times b equals big A, then those equations would be equal and we would be in good shape. This is a possible time to take a break. Let's substitute this first equation, b, into the second equation. So minus a times little a times big A equals big A. Well, that can only be true if minus little a squared was 1 or little a squared was minus 1. And that is possible for little a to be that. Little a could be plus or minus I. We know that I squared is minus 1 and minus I squared is minus 1. We'll see later that we need to take little a equals I to get a correct wave equation, the Schrödinger equation. Therefore, if little a is I, then b equals capital A times I for our wave function for a free particle in one dimension for the non-relativistic wave equation. So initially we thought that capital A and capital B could be totally independent. We didn't know if they could have real values or complex values, but we thought they were completely independent, and they were completely independent for the Klein-Gordon relativistic equation. But now we're seeing that in order to get a non-relativistic wave equation, which is first order in time, we have to constrain our initial wave function to have b equals ai. So let's substitute b equals ai back into the wave function. A cosine plus ai sine. Well, we could take the a out, and we get cosine plus I sine. Well, we know that we have an abbreviation for that, cis, and we also know that that's the same as this exponential function, a e to the I phi of x and t. Actually, we defined this exponential function to just be cosine plus I sine. So it's for sure the same. And we know what phi of x and t is because we had that earlier. So the wave function, capital psi of x and t, equals constant a, unknown, to be determined, e to the I quantity px minus et over h bar. This wave function is a valid wave function for the non-relativistic wave equation, Schrödinger equation. Now we want to show what that wave equation is. So wave functions for a free particle in one dimension for the non-relativistic wave equation are complex exponentials. They did not have to be for the relativistic wave equation. They could have been, but they did not have to be. But for the non-relativistic wave equation, they have to be complex exponentials. This is a possible time to take a break. Taking derivatives of exponentials is easy. We saw that earlier, that the derivative of e to the au is a e to the au. We can use that. We can get e times psi of x and t by taking this derivative. If we took the derivative of psi, here's psi, if we took that derivative with respect to time, it would add a prefactor of minus e over h bar, minus e over h bar, and we would get psi again. So we got the factor of e that we want, but we got this extra terms of minus e over h bar. Well, if we multiply minus I over h bar, if we put in an extra factor of I h bar will cancel. I times minus I is plus 1, so we will get e times psi. So we get the wave equation from e psi equals this term on the right that we've seen before. Now let's just substitute in this magic operator that will give us e psi. We get imaginary number I times h bar times the partial derivative of psi with respect to time equals minus h bar squared over 2m times the second derivative of psi with respect to x squared. This is the non-relativistic Schrödinger equation for a free particle in one dimension. The imaginary unit I on the left side, it comes from the derivative of the complex exponential wave function complex exponential wave function had I in the exponent. The imaginary unit I comes from the derivative of the complex exponential wave function, which we were required to use in order to get a non-relativistic wave equation with a first-order time derivative. Quantum mechanics will always need complex numbers. It will always have this I on the left side. Now, there's also this factor of -1 on the right side, and we will see later that that means that there's another imaginary number dealing with momentum. We'll see that later. We can get P times psi. Now that psi is a complex exponential, we could get P times psi. If we took the first derivative of psi with respect to x, we would get psi again, but we would pull out a factor of I times P over h bar. If we choose to multiply that by h bar over I, the h bars would cancel, the i's would cancel, we would get P. So it turns out that the momentum operator, P hat, is h bar over I times partial derivative with respect to x. We'll use this in future lectures. We're not going to use that in this lecture anymore, but notice that the complex exponential that we were required to use in order to get a non-relativistic wave equation, it gave us this operator P with an h bar over I. In most quantum mechanics books, they will tell you that this is the operator, and they may or may not show you why it has an I, why the I is in the denominator, why there is an I on the left side of Schrödinger equation. But we see now that it comes from the complex exponential, and we needed that in order to get a non-relativistic wave equation. This is a possible time to take a break. We can extend our free particle wave equation to 3 dimensions as follows. We're not going to prove this. The left side of the equation stays the same, IH bar partial derivative of psi with respect to t. On the right side, we replace the second derivative of psi with respect to x with an operator that's called del squared. This is a del squared. And in Cartesian coordinates, del squared is second partial with respect to x squared, which we saw earlier, plus second partial with respect to y squared plus second partial with respect to z squared. So it's not very difficult. Why do we use this del squared character when we could just write this? Because we're not always dealing in Cartesian coordinates. We might be dealing in cylindrical polar coordinates or in spherical coordinates. And del squared has a representation in those coordinate systems, which we can look up on Wikipedia or on the web. So it's more general to show the equation with del squared in it, and then we just pick up the form for del squared that we need for a particular coordinate system. Minus h bar squared over 2m del squared is the non-relativistic kinetic energy operator. We can extend our wave equation beyond a free particle by adding in the potential energy that the particle experiences. Here on the right side, we have the kinetic energy term, minus h bar squared over 2m del squared, and we add in a potential energy, which could be a function of position, x, y, z, and could be a function of time. And then we multiply that quantity times psi on the right side. This is the non-relativistic Schrödinger equation for a one-particle system, not including intrinsic spin angular momentum that we'll talk about in a later lecture. Now, how do we know we can do this? We don't. We just added this in and said this is right. The way we know is by solving problems with this form, getting results, and verifying against experimental results. And it is correct to add in the potential energy here like this. One more step. We're going to do one more abstraction. We're going to replace this entire quantity on the right with a new operator, h hat operator, where h hat is the Hamiltonian operator for a one-particle system. Just what we've identified before. So the Hamiltonian can be a function of position, x, y, z, and it can be a function of time. It's more abstract to just call it the Hamiltonian and we'll figure it out for any given problem. So this is the non-relativistic Hamiltonian and Schrödinger equation for a one-particle system, not including intrinsic spin angular momentum. This is a possible time to take a break. Now let's talk about energy levels. We're still talking about a free particle in one dimension. The free particle can have any non-negative value for energy, so greater than or equal to 0. This particle energy is a continuous quantity, not a discrete quantity. It's not quantized. These quantum states are unbound. They are not bound and localized in space for the free particle. We'll see later that generally for unbound systems, the energy will be a continuous quantity, not a quantized quantity. When we want to identify a particular energy level, we can include the subscript p for momentum, since a given momentum determines the given energy for a given mass. Energy is p squared over 2m. Now here we're going to allow momentum to be negative as well as positive. Earlier we said, oh, let's choose the x-axis so the momentum is positive, but we can relax that and we can allow momentum to be negative as well as positive for a given plus x-axis choice. So we can identify energy as E sub p, but you will also alternatively see the subscript k, k being the wave number determined by p equals h bar k. We're not going to talk more about this right now, but you will see both forms for a free particle, E sub p or E sub k. Now, here, momentum can be positive or negative, and so can the wave number. So the wave number is a signed quantity, and the wave number is a real number, not an integer. I know in many math problems we would use k to represent an integer, but in this use in quantum mechanics, k is a real number, not an integer. In future lectures, we will have bound states, not free particles, and they will have discrete quantized energy levels, and when we want to identify a particular level, we'll refer to it as E sub n, where n is an integer. Now, reversing the direction of momentum, negating it, does not change the energy because the energy is proportional to the square of the momentum. Therefore, a non-zero energy does not determine a single unique value for momentum. There's two values, plus and minus, square root of 2 times the mass times the energy. When we have more than one value, more than one state with the same energy level, we say that that energy level is degenerate, because the energy value alone does not uniquely determine a single state. And there are problems we will look at where the energy level is non-degenerate, it has a single state, and other problems where it is degenerate and has 2 or more states. This is a possible time to take a break. How is the matter wave a particle? We've got matter waves now. We've got a matter wave equation. We started from saying it was a free particle, a classical free particle in one dimension. Now let's go back and say, well, now that we know what the wave is, how do we reconcile it with the particle that we started with? We found the non-relativistic wave function for a free particle in one dimension with a definite momentum p. We found the wave function psi of x and t to be some constant a, which could be real or complex, times the complex exponential e to the I quantity px minus et quantity over h bar. The wave function is complex valued. It's a complex exponential. Let's take the magnitude of this complex valued wave function. Well, the magnitude of psi is just the magnitude of a, because the complex exponential, when we take its magnitude, we get 1. So the magnitude of psi is a constant, a real number, independent of space and time. The space and time dependence of psi was only in the phase of the complex exponential for a free particle. And so that space and time dependence disappeared when we took the magnitude. Magnitude of psi being independent of space and time means that this free particle with a definite momentum, represented by this plane wave function, is equally probable to be located anywhere in all of space. It's one-dimensional, so at any x value in space. This free particle with a definite momentum is everywhere in space, in x, and kind of nowhere because it's spread out everywhere. What's going on here? We could say that this wave function has zero uncertainty of momentum because we had a definite momentum, a single value p, but infinite uncertainty of location on the x-axis. It's equally likely to be anywhere. A classical particle with definite momentum would have a definite location in space at a given time. It would have a function x of t. We don't have that here. So how is this wave function a particle like the classical particle we started with? This is a possible time to take a break. The Schrödinger equation is linear in psi. Psi appears on both sides of the equation. If we have a valid wave function, valid psi, then 2 times it is also valid in the Schrödinger equation, and 10 times it is valid in the Schrödinger equation. If we have 2 different wave functions that satisfy the equation, so does adding them, or subtracting them, or any linear combination or superposition of those wave functions. Let's see what happens if we combine multiple wave functions with different values of momentum, and therefore different values of energy. Let's combine them and see if we get something like a classical particle. It's no longer going to have a definite energy. We have to give that up when we combine them. Let's see what we get. Let's start with just 3 values of momentum and see what the wave function looks like. We'll look at a single time. We'll take that time to be t equals 0. The wave function is complex valued, so it's difficult to represent graphically, so it'll be sufficient for us just to look at the real part of the wave function. We'll get enough information by looking at that. Here's the graph of a wave function psi, graph as a function of x for a single value of time t equals 0, where I took 3 definite values of momentum and I added their correct complex exponentials together, and then I took the real part. So we see that instead of being a cosine wave that's equal amplitude everywhere in space, we get these pulses, these beats. So a pulse is now more localized in space, but there's an infinite number of the pulses. So that's interesting. We've localized it, sort of, but also failed to localize it, sort of. It turns out we can get a single pulse by superposing not a few, not a finite number of wave functions, but an infinite set of momenta. If we combine them in a particular way, we can get a single pulse, a single Gaussian distribution in space by taking a Gaussian distribution of momenta. We're not going to do the math of that, but here's what that single pulse in space would look like. I'm just showing the real part here. it's most probable in this location in space, and it has some spread. And as you move away from where it's most probable, the probability of finding it decreases very rapidly and continues to decrease as you move away from the most probable location. And there's only one pulse in all of space. At time t equals 0, I'm showing it here. It would move in space and time. When we have this one pulse, we call this a wave packet. It's largely localized in space. It has a high probability of being here, or from here to here, or from here to here. So it has a high probability of being located in a small region in space at a given time. So it's somewhat like a classical particle. Certainly a lot better than what we had before. But there's still some finite uncertainty of location in space. It's mostly here to here, but it has some probability of being here, or very far away. There's always some finite probability of being anywhere. So there's some finite uncertainty of location in space, but also some finite probability of being located anywhere in space, including very, very far away from the peak. So it's more like a classical particle than a plane wave, but it's not the same as a classical particle. It does not have a definite location in space. This is a possible time to take a break. When we arrange a free particle wave packet Gaussian distribution in space and a Gaussian distribution of momenta, we have some uncertainty in position, delta x, and some uncertainty in momentum, delta p sub x. We're not going to define these precisely here, but we will do that when we study particle in a box in coming lectures. It turns out that no matter what you do or try, the product of these uncertainties for any problem, not just this free particle problem, the product of those uncertainties is greater than a universal minimum amount. Uncertainty in x times uncertainty in x momentum must be greater than or equal to h bar over 2. This relationship is called the Heisenberg uncertainty principle, which he discovered in 1927, so 2 years after the Schrödinger equation was published. You can make either of the uncertainties larger or smaller by technical means, physical means, but you cannot reduce the product below this value no matter what you do. So you can have a particle which is very localized in space by giving up localization in momentum. Or you can have a very definite momentum by giving up localization in space. But you cannot simultaneously know or measure the position and momentum of a particle both precisely. Can't do it. That's an important characteristic of quantum mechanics. And that's hard for us to get a good feel of when everything in the macroscopic world that we see from the time we're an infant looks like it has definite locations and definite speeds. We can cleverly arrange for the uncertainty product to be equal to the minimum, h bar over 2, at some given time. We can do that. We'll call that time t equals 0, and then as time advances from t equals 0, we will find that the spatial distribution of the wave function broadens in time. And so does the distribution of momenta, and the uncertainty product increases in time. And don't think that you can cleverly fool quantum mechanics by running time backwards to before time t equals 0. That spreads out the distributions as well and increases the uncertainty product. So we can pick a time and we can minimize the uncertainty product for a given time. But when we do that, it's going, as soon as we let time advance, it will start to spread out. Free particles cannot remain with the minimum uncertainty product. This is covered well in quantum mechanics courses and books. We won't look at this further. It involves a substantial amount of math and time and work, and it's, if you want to go further in quantum mechanics, you definitely need to do that, but we don't. We want to understand an introduction to quantum mechanics, so we're not going to look at this further for a free particle, but we will look at it carefully for a particle constrained to a box. It will be possible to do that with not a massive amount of math, and it will be worth doing. This is a possible time to take a break. Well, okay, so we got a wave packet, and that's better than a plane wave for imagining our classical particle, imagining its life in the quantum realm, the quantum world. But now that we have this wave packet, how does that square with macroscopic reality? I mean, a baseball isn't a wave packet, is it? Well, let's take an example of a smallish macroscopic particle, something that we could see. We could look at a bacterium under a microscope. Some bacteria are at the size limit of what we can see in a microscope, an optical microscope, not an electron microscope, an optical microscope. If we look at a bacterium, we don't see it spreading out in space or turning into waves. You can look as long as you want. It still looks like a bacterium. We see its position in the microscope. We could take measurements. We can calculate how uncertain we are of its position. We can measure its velocity by visual observations in the microscope. We could calculate how uncertain we think we are of the velocity. Say the bacterium mass is 10 to the minus 15 kilograms. Say we estimate its uncertainty in position as 1/10 of a micron over the time interval that we're willing to keep looking at it. To be consistent with the Heisenberg uncertainty principle, the uncertainty in its velocity must be greater than or equal to 5 times 10 to the minus 13th meters per second. You can do this math. You know what the value for h bar is. You can here we have the mass, we have the uncertainty in position. We can calculate the uncertainty in momentum. We can divide by the mass. We get the uncertainty in velocity. We know it must be greater than the amount from the Heisenberg uncertainty principle, so it must be greater than this amount. Well, is it or is it not? This would be 1 micron of travel in 22 days. And we are for certain only going to look at that bacterium for minutes. I mean, it would be excruciating if we continuously looked at it for an hour. We're not going to look at it for 22 days. This uncertainty in velocity is way smaller than we could ever estimate our velocity uncertainty by watching for a few minutes or an hour. We're not going to see the bacterium spread out like a wave packet. Its uncertainty in position times velocity, uncertainty in position times momentum is greater than or equal to h bar over 2, but because of its size and its mass, we're not going to see it looking like a wave packet, even though it is obeying the Heisenberg uncertainty principle. This is a possible time to take a break. Now, Schrödinger had expected that his wave equation would be able to describe classical particles behaving classically, behaving causally, cause and effect. But the free particle wave function we found didn't look like a classical particle to us. Niels Bohr was initially against attempting a space-time description of wave particles and against a causal description of quantum reality. He initially opposed solving quantum mechanics problems with differential equations. He thought that the quantum world just couldn't be described that way. But once Schrödinger's had published his Schrödinger equation and people thought about it, they had to interpret, what does the wave function mean? Bohr, Heisenberg, and German physicist Max Born, they came to develop what we now call the Copenhagen interpretation of probability distributions of measurements of quantum systems. The wave function is a probability amplitude Schrödinger, Einstein, and Dubrow, they became opposed to a probabilistic, non-deterministic interpretation of wave functions that satisfy the Schrödinger equation, but it seemed to be reality that for the quantum world, the wave function is probabilistic. Einstein proposed a number of very insightful cases to say that there must be an underlying determinism underneath quantum mechanics, even though we can't see it. And Bohr thought very deeply about Einstein's objections and came up with answers as to why quantum mechanics is truly the explanation of reality. And now we know that every experiment that we do, quantum mechanics is proven correct. Schrödinger later remarked that if he had known quantum mechanics would require probabilities and non-determinism instead of causality and trajectories, he would not have worked to develop the Schrödinger equation. This is the end of session C1.